Learning made easy, metallurgy for everybody, introduction to phase diagram, limited solubility in solid solution. In this video, we will discuss limited solid solubility solid solution, binary phase diagram, with example of lead and tin alloys. Other two we have already discussed in previous videos, link of which I have shared in description. First, completely soluble in solid solution. Example, copper and nickel alloys. Second, completely insoluble in solid solution. Example, cadmium and bismuth alloys. Consider that we heat lead element to the liquid phase. Then we cool it. When graph is plotted for temperature against time, it is observed that when it reaches crystallization temperature, that is 327 degrees Celsius, just below it, lead will start solidifying. Liquid phase will transfer to solid phase. Temperature will remain constant till entire liquid solidifies. Then metal further cools down. Same will be the situation for tin element. When tin is heated to liquid phase, then on cooling, just below crystallization temperature, that is 232 degrees Celsius, tin will start solidifying from liquid phase and will transform to solid phase. Temperature will remain constant till entire liquid solidifies, then metal further cools down. When alloy consisting of lead and tin with 10% tin heated to liquid phase, then on cooling just below liquidus line, solidification starts. As lead and tin are soluble in solid solution at this temperature, lead and tin solid solution formation starts. Common crystal structure of lead and tin atoms are formed. This solid solution is called as alpha solid solution. On further cooling, when it reaches below line separating liquid plus alpha and alpha solid solution, it will completely transform to alpha solid solution. It is saturated with tin atoms. On further cooling, as the temperature drops, solubility of tin atoms in lead decreases, due to which tin atoms move out of the crystals. It is known as precipitation or segregation. Now we have alpha solid solution and precipitates. Salvos line indicates partition between alpha and alpha plus precipitates. As the temperature drops further, more and more tin atoms will precipitate. When alloy consisting of lead and tin with tin 99% heated to liquid phase, then on cooling below liquidus line, solidification starts. Then crystals of lead and tin solid solution formation starts. On further cooling, when it reaches below line separating liquid plus beta and beta solid solution, it will completely transform to beta solid solution. As lead and tin are soluble in each other, in this we have common crystal structure of lead and tin atoms. On further cooling, as temperature drops, solubility of lead atoms in alloy decreases, due to which lead atoms move out of crystal lattices. This process is known as precipitation or segregation. Now we have beta solid solution and precipitates. Salvos line indicates partition between beta and beta plus precipitates. As the temperature drops further, more and more lead atoms will precipitate. For the Eutectic composition, that is 38% lead and 62% tin, when heated to liquid phase and cooled down, it will transform from liquid phase to solid phase directly. It is observed that when it reaches crystallization temperature, just below it, eutectic alloy, which is mixture of alpha and beta solid solution, will start solidifying. That is at 183 degrees Celsius. Liquid phase will directly transform to solid phase. temperature will remain constant till entire liquid solidifies. Then metal further cools down. Eutectic line for this alloy is from 19% tin to 97.5% tin at 183 degrees Celsius. When alloy consisting of lead and tin with 30% tin heated to liquid phase, then on cooling just below liquidus line, solidification starts. Then crystals of alpha solid solution formation starts. In the alpha solid solution, we have common crystals of lead and tin atoms, as tin and lead are soluble in each other. On further cooling, as the temperature reaches eutectic line, we have alpha solid solution and liquid phase having eutectic composition of components. As the temperature drops below eutectic line, the liquid phase transforms to solid phase. Temperature remains constant till entire liquid is solidified. Temperature further drops. Now we have alpha solid solution and eutectic mixture of alpha and beta solid solution. When alloy consisting of lead and tin with 80% tin heated to liquid phase, then on cooling just below liquidus line, solidification starts. Then crystals of beta solid solution formation starts, as the lead and tin are soluble in each other. In beta solid solution, we have common crystals of lead and tin atoms. On further cooling, as the temperature reaches eutectic line, we have beta solid solution and liquid phase having eutectic composition of components. As the temperature drops below eutectic line, liquid phase transforms to solid phase. Temperature remains constant till entire liquid is solidified. Temperature further drops. Now we have beta solid solution and eutectic mixture of alpha and beta solid solution. When alloying element percentage is less than the eutectic composition, it is known as hypoeutectic alloy. When alloying element percentage is more than in the eutectic alloy, it is known as hypereutectic alloy. Now we put all the cooling curves together and then draw the phase diagram for lead and tin alloy. Then this is how it will look like. Some lead tin alloy applications are general purpose solders and coating steel sheets during manufacturing corrosion resistant products. If you are interested to watch such videos on metallurgical subject, please subscribe to the channel. Topics discussed in this video are limited solid solubility solid solution, phase diagram, eutectic alloy, phase diagram of lead and tin alloy. Topic to be discussed in next video are iron carbon equilibrium diagram. Thanks for watching.